All right, thanks again. So we will continue on with the same speaker and move on to the paper Achieving Sub-Second Pairwise Query Over Evolving Graphs.
Okay. So this paper is about more traditional graph processing on the evolving graph. And this is a joint work with my collaborator in Tsinghua University and the University of Sydney and a startup company. So here in this paper, we mainly focus on the pairwise graph query. So obviously, like querying the evolving data with sub-second latency is very attractive for the for the real-time like OLAP system, but it's a very difficult job, and so it's very difficult to achieve the low latency. And in this type of the system, we have two kinds of like two types of the query. One is shown on this side. It is one-to-all. So here it is called a single source query. So we want to find out, for example, the shortest path from the source to the other, to all the other vertices. And in this case, we need to exhaustively check all the vertices. But another kind is the focus of this paper is a point-to-point, like pairwise query. So basically, it tries to answer what is the shortest path, for example, from the source to the destination. And in this case, we only need to look at a set of the vertices, right? And so in this, this type of the system is also the focus of some of like the recent work here. And this pairwise query has wide application. For example, in the navigation system, we want to find out the point-to-point like shortest path here. And for the internet design, we want to find the point-to-point, so we want to find the point-to-point, like the widest path to enable, the high bound width. And also for the graph, like clustering, we can enable, so we need to perform the point-to-point like BFS. So the current approach basically try to avoid the unnecessary computation by looking at the upper bound. And so basic idea is the following. So here we maintain the upper bound from the source to the destination, and based on the monotonicity property that is widely used in the application, we can actually avoid the unnecessary computation by this inequality. The problem here is that, for example, if we already know that the upper bound from the source to the destination is this number, and the question is whether we want to check the vertex V and the further pass from the V to D, right? Now, if, for example, the distance from S to V is already like larger, so it is if it is already like larger than the upper bound from S to D, then we don't need to check further. Okay, so this is the current state of the art. For example, the PMP paper estimated the tighter upper bound dynamically, like during the search, and they also try to decide whether to search from the source or the destination. Another system called the Tropolene, it is a single source like query system. It tries to get the better upper bound by the triangle inequality here. Okay, and in this paper we modify the system to make the system like perform the pairwise query. Based on this method, it can roughly reduce about half of the vertex activation, but we show in this paper it's not enough. So the main idea in this paper is to not only compute or consider the upper bound, but also the lower bound. So the idea is that if we know that the upper bound from S to D is like this value, but we also know a lower bound from V to D, right? So basically, we add more on this side, and so if this plus this is larger than that, we don't need to search. So it means that we compute more, okay? So that is the main idea. And in the result, we can show that we can reduce nearly 99% of the, so we can reduce nearly 99% of the vertex activation and achieve the significant like speed up. So to give you a concrete example, let's consider the simple graph here. And so in this graph, we know that the upper bound from S to D is 6, right? Now we are doing the query. And so based on the graph from S, we have the distance here. So all of them are smaller than the upper bound. So we need to go further. So we need to go further, right? So next step, what you can see is that here, in this case, from B, we don't need to look further because 5 plus 2 is already larger than 6. We don't need to check C. And similarly, from E to C, we don't need to go further because 2 plus 6 is also larger than 6, right? But if we do the upper bound plus lower bound using the same graph, what we can see is that, so we start from this 3, right? And suppose we have the lower bound, right? Suppose we have the lower bound, let's say from B to D, it's 5, right? So in this case, we can even pune the first step here, right? Because we know here is 5, and if 5 plus 5 is already larger than 6. And similar, we can pune the P2 as well. So basically, we can, if we consider the lower bound, we can compress the condition and avoid the activation earlier. Okay. Okay, so the question is how to estimate the tighter lower bound, right? So actually, it is quite intuitive, and it's ignored in the previous system. So basically, in the previous system, when they computed the upper bound, they used the triangle inequality here, right? So from S to D, it's used like a V, and so the upper bound of that is this one, right? Of course, it's so it can be changing so it can be changing based on selection of V. So the way that we compute the lower bound is simply to refactor this inequality and consider the factor here. So here we can compute the lower bound of S to D using this tool, right? And the insight of this is simply if you move this term on the left, you can see that it means that we go from V to S, and from S to D is larger than the V to D. So it's equivalent to the first. So we simply refactor that, and then we can use this tool to compute the lower bound. Okay. So, the idea is basically using this insight to establish a kind of a graph index. And this index is based on, so the index is computed based on the current status and a selection of the so-called hub. So the high-level idea is that using a graph, we can select one or more hubs, and we pre-compute so we pre-compute the standing query result here, okay? And we can use that information to compute the upper bound and the lower bound, and pune the computation at the runtime. Okay, so how do we maintain that lower bound and upper bound? And the change, so for example, if you change the graph, that information is also going to change. So this tool is also going to change. And the previous paper shows that it can, so that information can be computed incrementally. And if some part of the graph is changed, you can follow the dependency tree to update some part of the value in the graph. So in our system, we use 16 hubs to construct the graph index. Now, about the system, we also need to maintain several versions of the graph because conceptually we have a current graph, and so we have a version for the query, right? And the incoming update, including the including the addition and deletion, so it will also mutate the graph, and also we need to compute and update the graph index based on based on the mutated graph. So we need to do all the three things simultaneously. So here the idea is that we maintain several snapshots, and so basically the graph query is based on a previous version. that we already have the index and the graph structure. It is consistent. And then the index maintaining is performed, it's continuously performed based on the mutated graph. It takes some time, and we can, so we can put the updates in batch, right? And the current update is performed on this version. So this is to accept the update. And then when we update the index here, when we finish updating the index for a batch, we can move on to the next, so that the previously generated version with the consistent like graph index can be used for the graph query, right? So we can move up. And so essentially at any time we have 3 versions here. And so basically we have a notion of the data freshness. It's from the current to so it's from the current time to the time that the graph is updated. And so this can be efficiently implemented by 2 extra bits per edge. So for example, in this example, the blue edge is removed, and the red edge is the red edge is added. So what we can do is that if you remove the edge, so this bit, the red bit indicates whether the edge is in the closed snapshot, and this part indicates whether it is, so the red one indicates whether it is in the unclosed snapshot. The yellow one indicates whether it is in the closed snapshot. So if you remove one, it will become, so it will not be in the closed snapshot, but it's still in the closed snapshot. It means that at this point, if you run the query, it will still consider this edge as existing in the graph, right? And if you add one, oppositely, you can see that this will be in the unclosed snapshot. It means that we have not generated the index. So if you run the query, you will not see that, but later you will see that, okay? Okay, so here we build a system based on these ideas, and the snapshots is called sgraph, and the system maintains the index building and maintains, and also provide an interface so that the user can specify what you want to do when a vertex is activated, and more importantly, many applications need to redefine the operations for the different part for the inequality. So we allow the users to override that. And here it comes to the evaluation. So we use a 10-node cluster, and each one has 375 gigabytes memory and 24 cores. And we use this graph. So we try different applications, and you can see that for different applications, the abstract, add, subtract, and the greater than is reloaded into different operation, and that can be done in the programming interface. So this provides you the performance comparison between the PNP and the triplet. We modify that to support the Pairwise query. And you can see that the performance improvement is very significant, and that is purely because of the consideration of the lower bound. And this slide explains why we achieve the performance improvement. You can see that basically we look at less amount of the activation of the vertices, right? So the x direction is so the x-axis is so is the number of iterations. So over time you look at less number of the vertices here. So here we also try to understand the contribution of the speed up by the different optimizations. Specifically, we consider 3. One is to consider the upper bound, the other one is to consider the lower bound, and another one is to consider the bidirectional search. So we can either search from the source or the destination. And here is the result on the 4 graph, and you can see that basically, we need to consider the operations together. So if we consider the lower bound or the BS, it's always better than just to consider the upper bound. But these two is not clear which one is better. But if we, however, if we consider all of the three together, it is the best. So it means that it's important to consider the lower bound together with a BS, or bidirectional search. So finally, we want to report the result of the overhead of maintaining the index. So the experiment is designed in this way. Initially, the graph contains 70% of the initial graph, and then we divide the batch into the different sides. This is the ratio between the addition and deletion of the edges. And in this table, we can see that based on the batch size for the different algorithms, the time of updating the index is mostly smaller than a second. So unless the batch is very large. So it means that we can still provide very good freshness. Okay, so in conclusion, this paper proposed that when we consider the p-square, so when we consider like a pairwise query in the evolving graph, we should consider both upper bound and lower bound. And based on that, we build a system with the interface so with the interface, you can support the different graph algorithms, and the system is implemented with the snapshot. So the system is implemented with the snapshot-based decoupled architecture. Okay, that is the end.